It is shortly after 1 o'clock in the morning on July 25, 1943, and the sky above Hamburg has come alive with light. Master searchlights, each one drawing 200 amperes through a beam of nearly 1 billion candela, sweep the darkness with the precision of a conductor's baton. On the ground, German radar operators sit hunched over their cathode ray tubes, waiting for the telltale blip that means a British bomber has entered their sector. For 3 years, this system has worked. Tonight, it does not. Inside the cockpits of the lead Lancasters and Sterlings, navigators glance at their watches and begin feeding bundles of something extraordinary through the flare chutes, 1 bundle every minute, timed by stopwatch. The bundles are nothing more than scraps of blackened paper backed with aluminium foil, each strip 27 centimeters long and 2 centimeters wide, no heavier than a handful of confetti. They tumble out into the slipstream and begin to fall, twisting and fluttering through 10,000 feet of night air. On the ground, the effect is immediate and total. The radar screens that have guided Germany's night defenses since 1940 fill with thousands of false echoes. Operators who moments before could pick a single bomber out of the darkness now stare at a blizzard of static, unable to tell a 4-engined Lancaster from a scrap of tinfoil drifting on the wind. The master searchlights, slaved to that radar, begin to swing wildly across the sky, illuminating nothing, chasing ghosts. Anti-aircraft guns that depended on the same data fire blind, their shells bursting in empty air thousands of feet from the nearest aircraft. This is window, and on this night it does something no fighter aircraft, no armor plating, and no amount of evasive flying had managed to do consistently across 3 years of bomber war. It makes Germany's entire integrated air defense system, the most sophisticated network of its kind on Earth, simply stop working. Bomber Command will lose 12 aircraft out of 791 that took off. In previous raids against similarly defended cities, losses of 5 or 6% had been considered acceptable. Tonight, the loss rate falls to under 2%. A handful of British scientists working with paper, foil, and an understanding of basic physics have just rendered a city's worth of radar, searchlights, and flak guns close to useless in a matter of minutes. To understand why that mattered so much, you have to understand just how desperate the war in the night sky had become. By the summer of 1943, RAF Bomber Command was losing aircrew at a rate that mathematically made survival to the end of a tour of operations a matter of luck rather than skill. A bomber crew flying a standard tour of 30 operations faced odds of survival that hovered grimly at roughly 1 in 3. The cause was not mainly enemy fighters, though those exacted a terrible toll of their own. It was the integrated system the Germans had built to find, illuminate, and destroy bombers in total darkness, a system the Allies came to call the Kamm-Huber line. That system worked in layers. Early warning radars, codenamed Freya, watched the approaches from Britain and could see aircraft forming up over East Anglia from across the North Sea. Once a raid was detected, the information passed to a network of control sectors, each built around a more precise tracking radar called Würzburg, accurate enough to guide both anti-aircraft guns and searchlights directly onto a target. A second Würzburg would lock onto the approaching night fighter, and a ground controller, watching both plots converge on an illuminated table, would talk the fighter pilot onto the bomber's tail. It was an assembly line for shooting down aircraft, methodical, repeatable, and devastatingly effective. By early 1943, a single well-coordinated sector could expect to find and destroy multiple bombers on any clear night, and Bomber Command's loss curve was bending in the wrong direction. The maddening part, for British scientists, was that none of the existing countermeasures solved the underlying problem. Tinsel, introduced in December 1942, jammed German fighter control radio with engine noise broadcast from microphones fitted in the bombers, and it helped, but pilots could still be guided by other means. Mandrel jammed the early warning Freya radars with broadcast noise, buying the bomber stream valuable minutes of surprise, but it did nothing once a raid had been detected, and the more precise Würzburg sets took over. These were all what engineers call point solutions, clever answers to one part of the problem that left the rest of the machine running. What Bomber Command needed was something that did not just jam one type of set, but blinded the entire family of radars on which the German system depended: the early warning sets, the gun-laying sets, and the night fighter's own onboard radar, all at once, cheaply, and from every aircraft in the stream simultaneously. On paper, that sounded close to impossible. A single transmitter powerful enough to jam every radar frequency in use would have been enormous, fantastically expensive to produce in quantity, and instantly vulnerable to the simplest of countermeasures: changing frequency. The air staff needed a way to create false targets, not loud noise, and they needed it to be so simple that an exhausted wireless operator, flying through flak at 15,000 feet, could deploy it correctly every single time. The strange truth was that the answer had been sitting in a drawer at the telecommunications research establishment for more than a year, judged too dangerous to use. The idea traced back to 1937, when researcher Gerald Touch, working alongside the radar pioneer Robert Watson Watt, wondered aloud whether lengths of wire dropped from balloons might overwhelm a radar receiver with false echoes. Around the same time, the physicist R.V. Jones suggested that falling strips of metal foil might do precisely the same thing. The principle, once understood, was almost insultingly simple. Cut a strip of metal to roughly half the wavelength of the radar you wish to confuse, and that strip will resonate like a tuning fork struck by the radar's own pulse, re-radiating the signal back at the receiver as though it were a solid object. Drop enough of these strips together, and a radar set sees not one aircraft, but thousands. It was the Telecommunications Research Establishment, based at Malvern in Worcestershire, that turned the idea into a weapon. The work fell largely to Joan Curran, the only female scientist on the TRE's research staff who had studied physics at Cambridge before the war, at a time when the university would not even award women a formal degree. Curran experimented with cutting copper foil into strips and bundling them into makeshift ladders, testing the results against a ground radar station on a Saturday morning in 1942. Early proposals had been almost comically inventive. Someone suggested printing the strips with propaganda messages so they could double as leaflets on the way down. In the end, simplicity won. The most effective design that emerged from these trials was a strip of black paper backed with aluminum foil, cut to exactly 27 centimeters by 2 centimeters, the dimension chosen specifically to resonate at the wavelength used by the German Würzburg radar. Bundles of these strips, each parcel weighing about half a kilogram, were packed for easy handling and rapid release through a bomber's flare chute. The head of the TRE, AP Row, gave the device the deliberately unremarkable codename Window. What made Window so unsettling to use was not its complexity, but its cost. A device built almost entirely from kitchen cupboard materials, foil, and paper, manufactured by the ton in ordinary British factories, was capable of neutralizing radar systems that had taken Germany years and enormous resources to build. British intelligence had confirmed just how vulnerable those systems were after the Bruneval raid of February 1942, when a small party of paratroopers seized components of a German Würzburg set from the French coast and brought them back to England for examination. That captured equipment confirmed that German radar operated across a narrow handful of frequencies. Every one of them a target Window could be tuned to defeat. By the spring of 1942, scientists at the TRE had calculated that bundles released from 10,000 feet would produce a cloud of false echoes capable of masking an aircraft for roughly 15 minutes, more than enough time to render any precision tracking by Würzburg, whether for guns, searchlights, or fighter direction, essentially impossible. And that finally brings us back to the searchlights themselves. By 1943, the most powerful German searchlights, the 200-centimeter Scheinwerfer 43 models, could throw a beam rated at well over 2 billion candle power, powered by generators the size of a small lorry, capable of finding a target 13 kilometers away. These so-called master lights worked in concert with smaller 150-centimeter lights arranged in a triangle around them, the master light finding the bomber by radar and the others coning in to hold it fixed in a column of white fire, a column from which an anti-aircraft gun or a waiting night fighter rarely missed. It was an experienced aircrew described as being caught utterly naked in the sky, blinded, dazzled, and stripped of the cover of darkness that was a bomber's only real protection. Window did not jam the searchlight. It did not need to. It simply fed the radar that aimed the searchlight a sky full of phantom targets, and a weapon that depends entirely on knowing precisely where to point becomes worthless the moment it cannot tell truth from static. Window's first operational use came on the night of 24th and 25th July 1943, as the opening blow of Operation Gomorrah, the sustained assault on Hamburg that Bomber Command's chief, Arthur Harris, had finally secured permission to launch from Winston Churchill himself just 9 days earlier. Crews from 76 Squadron were among the first trained to use the device, briefed to release one bundle every minute by stopwatch through the flare chute, a task simple enough to perform under fire and reliable enough that even a frightened, exhausted crew could not easily get it wrong. The results that first night were, in the words of those who witnessed them, spectacular. German radar operators reported screens filled with echoes that bore no relation to anything real. The master searchlights, slaved to radar that could no longer distinguish bomber from foil, wandered aimlessly across the night sky, illuminating cloud, smoke, and nothing at all. Anti-aircraft batteries, denied accurate data, fired into empty darkness in a pattern crews came to call, with grim humor, the unaimed barrage. Records from the German side, understandably, are less complete than the British accounts of triumph, since admitting the scale of the failure was hardly something Luftwaffe controllers wished to commit to paper for their superiors. What is documented is the casualty figure. Of the 791 aircraft that took part in that first Hamburg raid, only 12 failed to return, a loss rate dramatically below what crews had come to expect from a target of that size and importance. Bomber crews who flew subsequent raids during the Hamburg campaign described the noticeable absence of the usual coordinated cone of light, the searchlights instead sweeping in slow, confused arcs that bore no relation to the bomber's actual track. Squadrons soon had purpose-built chutes fitted specifically for faster window deployment, and aircrew, recognizing a rare technological advantage in a war that had given them precious few, began competing to fly as many operations as possible before the Germans found a counter. If you are finding this interesting, a quick subscribe helps more than you know, and there is a great deal more to this story still to come. The Germans were not, in fact, ignorant of the principle behind window. German scientists had independently developed an almost identical device, which they called Duppel, named after the Berlin suburb where early trials had taken place. For more than a year, in one of the war's strangest standoffs, both sides possessed a weapon capable of blinding the other's entire radar network, and both refrained from using it, each terrified that revealing the trick would simply hand the enemy a working blueprint. Britain's chief scientific advisor, Professor Frederick Lindemann, warned explicitly that using window against Germany would only invite the Luftwaffe to copy it and unleash a renewed blitz against British cities. It took the mounting pressure of Bomber Command's casualty figures and Harris's persistent lobbying to finally tip the balance in July 1943. When the Germans did retaliate with Duppel, beginning with a raid on the night of 7th and 8th October 1943, their strips were cut to 80 centimeters by 1.9 centimeters, tuned to the wavelengths used by British gun-laying radar rather than the shorter Würzburg wavelength the British version targeted. Duppel allowed a brief resurgence of German bombing over London during the early months of 1944, in a campaign nicknamed the Baby Blitz. But by then the comparison was no longer close. Britain's night fighter force had grown enormous and increasingly capable, equipped with its own airborne radar that, unlike the ground-based German system, could often still pick out a genuine contact within the chaff cloud at close range. The relatively small number of German bombers available for the effort meant Duppel's protective effect, however real, was overwhelmed by simple weight of numbers on the British side. The Americans, briefed on the British discovery through the Tizard mission, developed their own version under the name Chaff, credited separately to the astronomer Fred Whipple and naval engineer Merwin Bly, though early American trials suffered from strips that clumped together and fell uselessly rather than dispersing into an effective cloud. It would take further refinement before the United States Army Air Forces adopted the British approach more fully for their own daylight campaigns. What set the British version apart, in the end, was not cleverness so much as decisiveness rooted in production capacity. Britain could manufacture window by the ton in existing paper and foil plants, distribute it to squadrons within weeks, and train crews to use it with nothing more than a stopwatch and a flare chute. Germany, fighting a multi-front war with steadily tightening resources, found it harder to scale Duppel production and distribution fast enough to matter strategically once the British night fighter advantage had grown so large. The fundamental physics were identical on both sides. The difference was who could turn the idea into millions of strips in the hands of thousands of aircrew fastest. The material legacy of window is, by most serious assessments, somewhat smaller than its psychological one. It did not win the bomber war on its own, and historians continue to debate exactly how much of Bomber Command's reduced loss rate through late 1943 should be credited to window itself versus the broader package of countermeasures, tactics, and growing electronic warfare expertise deployed alongside it. The Germans adapted within months, training operators to recognize the visual signature of a chaff cloud against a moving fighter contact, and pushing more Würzburg sets into service to maintain redundancy. What is not in dispute is the sheer scale of the demonstration. A piece of technology costing almost nothing to produce had, in a single night, exposed the fragility of an air defense network that had taken Germany years to build, and that depended entirely on radar data nobody had previously thought to falsify so cheaply. The psychological effect on German controllers, suddenly unable to trust their own instruments, persisted long after engineers found partial technical fixes, and the broader lesson that an integrated, centralized defense system has a single point of failure in the data it trusts, would echo through electronic warfare doctrine for the rest of the 20th century. Windows' influence did not end with the war. The same principle, a cloud of resonant strips defeating a radar by flooding it with false targets, remains in active military use today under the name Chaff, deployed from aircraft and warships using the same half-wavelength logic that Joan Curran tested with copper strips on a Saturday morning at Malvern. Modern radars, capable of distinguishing a slow-falling cloud of foil from a fast-moving aircraft using Doppler shift, have forced further refinements, but the basic countermeasure these scientists devised in 1942 has never been fully retired. Surviving examples of original window bundles, along with the wireless and radar equipment it was designed to defeat, can today be seen in the collections of the Imperial War Museum and at the Defford Airfield Heritage Site in Worcestershire, close to where the device itself was first conceived. Picture, once more, that night above Hamburg, the searchlights swinging in slow, useless arcs across a sky empty of anything they can actually find, the radar screens below choked with thousands of phantom targets, the anti-aircraft guns firing blind into darkness while the real bombers pass overhead largely untouched. 3 years of German engineering, vast investment in radar stations, generators, and crews, undone in minutes by paper and foil that cost a fraction of a single bomb. That is the story of Window, and it is worth sitting with the strangeness of it. The most sophisticated air defense system on the planet, built from cavity magnetrons and precision ground optics and years of careful coordination, brought low not by a bigger gun or a faster fighter, but by an exact understanding of a single number, the wavelength its own radar used to see. This was not brute force triumphing over cleverness. It was the reverse. A handful of scientists working at a research station in the Worcestershire countryside looked at the most advanced electronic battlefield system of its age and found, in its own physics, the seed of its undoing. They built that seed from rubbish bin materials, paper, and foil, and the most lethal sky in Europe was, for one extraordinary night and many nights after, simply switched off. The searchlights kept burning. They just stopped finding anything. And in that gap between light and sight, between a system that worked perfectly and a system that could no longer tell truth from shadow, thousands of young men flying through the dark found, however briefly, a fighting chance they had not had the night before.